Hello everyone, my name is Solomon Matthew, and today I'll be presenting on Markov Chain Monte Carlo and the Metropolis-Hastings algorithm. So the core question behind this presentation will be, how can we compute expectations under a probability distribution that is known only up to a constant and that is impossible to directly sample from? So this is a question that shows up constantly in Bayesian statistics, probabilistic machine learning, and computational science. So in this presentation, I'll go from the basic notation to Markov chains and stationarity, to the derivation of Metropolis-Hastings, to the detailed balance proof, to some worked examples, mixing behavior, effective sample size, and then to a more advanced operator viewpoint. So the idea here is not just to present the Metropolis-Hastings algorithm by itself, to describe it, but to also explain why it works mathematically. So the first slide will be looking at the target distribution and the notation. And you'll notice on this slide, every symbol is important because it explains why Markov chain Monte Carlo is required or is needed in the first place. So we'll begin with the target density, which is denoted as pi of x. So here x is a candidate state or a candidate parameter value, and the quantity pi of x is the normalized target density, meaning it is the actual probability density that we would like to sample from. But the issue is that in most realistic problems, we don't know this density in the normalized form, but we do know pi tilde of x, which is the unnormalized density. But this only tells us the relative weight and not the actual normalized probability. To turn pi tilde of x into a proper density, we need to divide by z, which is the normalizing constant, which makes the total mass equal to 1. So the Bayesian instance on the right side of the slide is also important. We write it as pi of theta given y proportional to p of y given theta times p of theta. So here, theta is the unknown parameter, y is the observed data, p of y given theta is the likelihood, p of theta is the prior, and the proportionality sign means equal up to a constant. So the obstacle is pretty much that constant. In most realistic models, the integral defining z doesn't have a closed form, or it becomes too expensive to compute in high dimensions. And this is where Monte Carlo, the Markov chain Monte Carlo, gets around by constructing a stochastic process whose long run distribution is the target distribution pi. So in this slide, we'll look at ordinary Monte Carlo versus Markov chain Monte Carlo. And this slide also explains the computational goal. So usually the real task is not sampling for its own sake. The real task is computing an expectation under the target distribution, right? So we write the expectation under pi of f of x. So the function f of x can represent any quantity of interest. It could be mean, it could be variance, probability, an indicator function, a prediction. So if we had independent and identically distributed samples, meaning x1 through xn are independent and identically distributed from pi, then we could use the sample average to approximate those expectations directly. But the entire problem or the issue is that direct, independent, and identically distributed sampling from pi is usually impossible. So Markov chain Monte Carlo replaces that impossible direct Monte Carlo setup with a Markov chain, which is denoted here as x0, x1, x2, and so on, whose stationary distribution is pi. Then instead of an independent and identically distributed average, we use the ergodic average along the chain to estimate the same expectation. So the trade-off here is that the samples are dependent. And this dependence is the price that we have to pay for this entire thing to become feasible. And that is sort of the conceptual difference between ordinary Monte Carlo and Markov chain Monte Carlo. Direct Monte Carlo requires easy sampling, while Markov chain Monte Carlo only needs a transition rule, in essence, that preserves pi. So moving on to the next slide, we're going to be looking at Markov chains, transition kernels, and stationarity. So this slide pretty much talks about the probabilistic machinery behind um, Markov chain Monte Carlo. So first is the Markov property. So what is that? A Markov chain forgets the past beyond the current state. Formally, once x sub t is known, the conditional law of the next step does not depend on earlier history. So the future depends on the present, not the full past. Next, let's look at the transition kernel, which is written as p of x comma a. Here, x is the current state, a is a measurable set of possible next states, and p of x comma a is the probability of moving from state x into the set A in one step. And this is the formal object that defines the chain's dynamics. Then we must also define the stationary distribution. So a distribution pi is stationary if whenever x sub t is distributed according to pi, then x sub t plus 1 is also distributed according to pi. So stationarity is an equilibrium condition. It means that the distribution is preserved by the kernel. So in a discrete state space, this becomes pi sub j equals the sum over I of pi sub I times p sub I j. That is the balance equation in matrix form. So for Markov chain Monte Carlo, stationarity is essential because we want the chain's equilibrium law to be exactly the target distribution. So looking at the next slide, ergodicity. This slide pretty much explains why stationarity alone isn't enough, and the chain must actually approach pi from arbitrary starting points. So it is not sufficient just to have a chain that preserves pi if the chain never actually reaches pi from arbitrary starting points, which is why we need ergodicity. So the slide breaks down ergodicity into three key properties. First is irreducibility, meaning every relevant region can eventually be reached from every starting state. So the chain cannot get trapped in some isolated subset of the state space. Second is aperiodicity, meaning the chain isn't stuck in a deterministic cycle. And third is positive recurrence, meaning the chain returns often enough for stable long-run frequencies to exist. Under these conditions, we get the convergence in law starting from a point x. The distribution after t steps approaches the target distribution pi as t goes to infinity. And once that is true, the ergodic theorem tells us that the empirical averages along one dependent trajectory converge to the correct expectation under pi. And that theorem is the real mathematical justification for Markov chain Monte Carlo estimation, and it explains why one long dependent run can still give us correct estimates. So this is the design problem. So we need to construct a kernel that preserves pi. So the central question is no longer how do we sample from pi directly, and so the question becomes how do we design a valid transition rule or a valid kernel that preserves pi. So there are three desired properties listed here. First is invariance. Pi needs to be stationary for the kernel P. Second is ergodicity. Chain must actually converge to pi from arbitrary starting points. And third is computability, meaning we should be able to evaluate the transition rule using only the unnormalized target, which is pi tilde. So the slide then introduces a very sort of convenient sufficient condition called detailed balance. So detailed balance says that in equilibrium, probability flow from x to y exactly matches probability flow from y back to x, and this property is called reversibility. It is stronger than stationarity, but the reason that it's so useful is that if the detailed balance holds, then stationarity follows automatically. And Metropolis-Hastings is designed exactly around this idea. It chooses an acceptance rule such that detailed balance is satisfied, or it holds. So coming to the next slide, here we'll be looking at the Metropolis-Hastings algorithm. So we begin at the current state, right? And we set x sub t equals x. Then we generate a proposal denoted y from the proposal distribution q of dot given x. More concretely, q of y given x is the proposal density, meaning it tells us how the candidate state y is generated from the current state x. Then the acceptance probability is computed, which is written as alpha of x comma y equals the minimum of 1 and pi of y times q of x divided by pi of x times q of y given x. So every symbol here matters. X is the current state, y is the proposed state, q of y given x is the forward proposal probability or density, q of x given y is the reverse proposal probability or density, and alpha of x comma y is the probability of accepting the proposed move. So after that, we draw u from the uniform distribution on 0 to 1. And if u is less than or equal to alpha of x comma y, then we accept the move and set x sub t plus 1 equals y. Otherwise, we reject the move and we keep the old state. So x sub t plus 1 equals x. So the proposal suggests a move, but the accept reject correction is what makes the chain so exact or accurate. So here we'll go into why normalizing, the normalizing constant cancels. So one of the most important facts in the entire presentation is if we substitute pi of x equals pi tilde of x divided by z into the Metropolis-Hastings acceptance ratio, then the unknown constant z appears in both the numerator and denominator. And because of that, it cancels exactly. And this means that the Metropolis-Hastings only needs relative density values and not the full normalized density. And this is what makes the algorithm so useful. In Bayesian inference, the same thing happens with the posterior, right? So we have the pi of theta given y proportional to p of y given theta times p of theta divided by the evidence of p of y if fully normalized. But the evidence p of y never appears in the final ratio. So the posterior sampling remains feasible even when the marginal likelihood is intractable. So that's why Monte Carlo Markov chain, or Markov chain Monte Carlo, becomes such a central sort of tool in Bayesian computation. And now looking at the next slide, we're going to look into a sort of detailed balance proof step by step. So the main idea here is that the acceptance rule is engineered such that the forward flow equals the backward flow. For x not equal to y, the off-diagonal transition density is q of y given x times alpha of x comma y. And if we multiply by pi of x, we get pi of x times q of y given x times alpha of x comma y. Now we substitute the definition of alpha, which gives pi of x times q of y given x times the minimum of 1, and pi of y times q of x given y divided by pi of x times q of y given x. So algebraically, this simplifies to the minimum of pi of x times q of y given x and pi of y times q of x given y. And this right here is the key point. The expression is symmetric in x and y. So if, to put it in other words, once the accept rejection correction is applied, the pairwise probability flow becomes reversible. And that's the symmetry that the proof here is trying to create. So looking at part 2 of the detailed balance proof, from the symmetry identity on the previous slide, we get that pi of x times q of y given x times alpha of x comma y equals pi of y times q of x given y times alpha of y comma x for y not equal to x. And that is exactly the detailed balance relation for the non-state put moves. So the remaining probability mass is assigned to staying at x. This ensures that total probability is preserved. Then stationarity follows by integrating over x. So in other words, if we integrate pi of x times p, a large P of x, comma d y over x, the derivative, so pi is invariant for the Metropolis-Hastings kernel pi. So this is why the algorithm is exact. It does not merely, it doesn't just drift towards region of high density. It preserves the full target distribution. And that's the important distinction here. A greedy optimization algorithm tries to move uphill, but the Metropolis-Hastings does something more subtle. It creates the correct equilibrium law. So moving on to the next slide, we're going to be looking at a worked example. So this slide will give us a concrete example, so we can see how the accept reject mechanism shapes the movement. So the target distribution is the standard normal. So pi of x is proportional to e to the minus x squared over 2. So the proposal is a Gaussian random walk, meaning that the proposed value y given x sub t equals x is distributed as a normal with the mean x and variance sigma squared. Because this proposal is symmetric, meaning q of y given x equals q of x given y, the Hastings correction cancels. So the algorithm reduces the original Metropolis rule. The acceptance probability becomes the minimum of 1, and the ratio of the target density at y to the target density at x. So for the normal target, that becomes the minimum of 1 and e to the minus quantity y squared minus x squared over 2. And this gives us a very sort of intuitive interpretation. So if the proposed point y is closer to 0 than x, such that its absolute value is smaller, then the move goes toward the high density center and it is always accepted. But if the proposed point is further from 0, then it is still accepted sometimes, but not always. And this is something crucial because it prevents the chain from collapsing into just pure optimization. It still explores the full distribution. So look in this slide, we're going to look at a Bayesian worked example and show exactly how likelihood times prior enters the Metropolis ratio. So suppose the observed data comes from a normal model with an unknown mean theta. The likelihood depends on theta through the observed data, and we also specify a prior distribution on theta. Combining those, the posterior density is proportional to likelihood times the prior. The important point is that even if the posterior is not analytically convenient, the unnormalized posterior is easy to evaluate at any candidate theta. Then we use a random walk proposal of the form theta prime equals theta plus epsilon, where epsilon is the normal with the mean 0 and variance s squared. But because the proportional is symmetric, only the posterior ratio remains in the acceptance probability. So in each accept-reject step, what is evaluated numerically is the ratio of the posterior at the proposed theta prime to the posterior at the current theta. And this is a great example because it shows how the Metropolis-Hastings operates in a real Bayesian setting. The likelihood times prior gives the target up to a constant, and symmetry in the proposal makes the acceptance step very, very simple. Moving on to the next slide, we're going to be looking at the estimation from the chain, burn-in, autocorrelation, and effective sample size. So the chain is valid asymptotically, but dependence changes the variance story. So the first formula on this slide is the ergodic estimator, meaning the average of f of x sub t along the chain. And that's the quantity that we use to estimate the expectations under pi. So the slide also mentions burn-in, which means discarding early iterations if the chain has not reached its typical region. So the idea is that the beginning of the chain might still reflect the arbitrary starting value. So sometimes it's often discarded, or some of the initial segment is discarded. And also next is the asymptotic variance. Because the chain is dependent, the variance of the estimator is not the same as in the independent and identically distributed case. Serial correlation inflates uncertainty. If the chain mixes slowly, then we get fewer effectively independent draws, even if the raw sample size looks large. That's why the concept of effective sample size, or the first slide it was called ESS, is so useful because ESS translates the dependent chain into an equivalent independent and identically distributed sample size. So Markov Chain Monte Carlo is first about correctness, but it also takes into consideration efficiency. So slide 14 is about proposal tuning, mixing, and high-dimensional difficulty. So a Markov chain can be perfectly correct mathematically and still be inefficient if the if the proposal distribution is badly chosen. So if the proposal steps are too small, then the chain has a high acceptance rate, but it only makes tiny local moves. This then leads to a strong autocorrelation and slow exploration of the state space. On the other hand, if proposal steps are too large, then many proposals land in low density regions. Rejection becomes frequent, the chain can stick, and computation is wasted. So there is a sort of trade-off that is present in proposal tuning. And also we can see in the slide that high dimensions are very difficult. In high dimensional spaces, probability mass often concentrates on thin regions, and naive random walk proposals scale poorly. And that's why geometry-aware samplers were developed, such as Gibbs sampling, Langevin methods, and Hamiltonian Monte Carlo. The practical sort of message here is that proposal design controls mixing speed, but Metropolis-Hastings accept reject step still provides the exactness that we're looking for. So finally, to the last slide, looking at a sort of advanced mathematical viewpoint and the final takeaways. The operator viewpoint defines Markov operator uh, P acting on a function f, and under reversibility, P is self-adjoint on L squared of pi. That functional analytic viewpoint opens the doors to studying convergence using spectral gap eigenvalues and other um, theoretical tools. So Metropolis-Hastings is connected not only to probability and statistics, but also to many other fields such as functional analysis. So this slide also lists other important extensions such as Gibbs sampling, Hamiltonian, Monte Carlo, Langevin sampler, pseudo-marginal MCMC, and reversible jump MCMC. All of these are sort of built off the same general philosophy that they want to adapt to different structures and computational settings. And the 5 main takeaways that would summarize this entire presentation would be: first, Markov Chain Monte Carlo replaces direct sampling by a Markov chain. Second, Metropolis-Hastings works because it enforces detailed balance. Third, normalizing constants cancel. Fourth, ergodicity justifies averages along the chain. And fifth, mixing determines practical efficiency. So the sort of bottom line here is Metropolis-Hastings is not just a sampling trick. It is a carefully designed reversible stochastic process whose equilibrium law is exactly the target distribution. And that is exactly what denotes or gives it its importance and sort of its beautifulness. Thank you all for listening. I appreciate your time.